Hello everyone. In this video, we will be discussing data representation using numeric and non-numeric. So first, for the numeric data representation, this will be divided into two parts. The first part, we will be discussing unsigned numbers and signed numbers. The second part, we will be discussing fixed point numbers together the floating point numbers. So let's begin with the unsigned numbers and signed numbers. The first is the binary coded decimal. The binary coded decimal, or BCD, uses 4-bit binary representation for each decimal digit. Remember that it is each decimal digit. This is unsigned, therefore, we do not take into consideration whether the given number is positive or a negative number. It is also called the 8421 code because it follows a positional weight 8, 4, 2, and 1. Here we have the BCD format of the digits 0 to 9. And remember that the available maximum digit value is only 9. So we can only represent the digits 0 to 9 in BCD format. So let's try to explain how did we get these values using the 8421. So we have 8, 4, 2, and 1. So let's try with number 3. We have 0, 0, 1, 1. So 0, 0, 1, 1. To get that, all we have to do is add 8, 4, 2, or 1, and the sum should be equivalent to the digit. In this case, we have 2 plus 1 is equals to 3. That's why we got 0, 0, 1, 1. Let's try another one. 7. We have 0, 1, 1, 1. In this case, 4 plus 2 plus 1 is equals to 7. That's why we got 0, 1, 1, and 1. Let's try 9. We have 1, 0, 0, 1. 8 plus 1 is equals to 9. That's why we got 1, 0, 0, 1. So let's try some examples on how we will get the BCD format. So for the first example, let's try to get the BCD format of 420. So let's have the 8421 table here. 8421. So for the first digit, we have 4. It is simply 4. So we will be having a BCD 0, 1, 0, and 0. The next digit is 2. So we have 0, 0, 1, 0. And the last digit is simply 0. So we do not need to add anything. So it will be 0, 0, 0, and 0. So the final answer will be this one. Let's try another example. Let's try to get the BCD format of 1763. So again, let's have 8, 4, 2, and 1 here. So the first digit is 1. So the BCD of 1 is 0, 0, 0, and 1. And the second digit is 7. So we know that 4 plus 2 plus 1 is equals to 7. So we will have a BCD 0, 1, 1, and 1. The next digit is 6. And again, 4 plus 2 is equals to 6. So our BCD for 6 is 0, 1, 1, 0. The last digit is 3. And we will have 2 plus 1 is equals to 3. So the BCD is 0, 0, 1, 1. So our final answer will be this. So that is binary coded decimal or BCD. Let's move on with unpacked decimal format. The unpacked decimal format or UDF uses 1 byte or is equivalent to 8 bits binary representation for each decimal digit. Again, this is for each decimal digit. So for the syntax, the first bits contains the zone bits or the sign bits. And the remaining 4 bits is represented using the BCD format. In this case, it indicates the sign, so the sign is placed together with the last digit. For positive numbers, the sign bit will be 1100, and for the negative numbers, the sign bit will be 1101. For the zone bits, it is always constant and the value for zone bits is 1111. So let's try some examples to apply the UDF. So let's try to find the UDF of positive 176. So we have 1, 7, and as we said, the sign bit is placed together with the last digit, so it will be positive 6. So for the first 4 bits, it contains the zone bits, which is constant, and the value of zone bits is 1111. And the BCD format of 1 is 0, 0, 0, 1. For the next digit 7, again, zone bits first, 1. And the BCD format of 7 is 0, 1, 1, 1. Here, for the last digit, we have the sign bit first. The value of the sign bit for positive is 1, 1, 0, 0. And the BCD format of 6 is 0, 1, 1, 0. So our final answer will be this. Let's try another example. Let's try the UDF of negative 2564. So we have 2, 5, 6, and again the sign is together with the last digit, negative 4. So again, zone bits first. And the BCD format of 2 is 0, 0, 1, 0. Again, zone bits for the next digit. Then the BCD format of 5 is 0, 1, 0, 1. For the third digit, again, zone bits. And the BCD format of 6 is 0, 1, 1, 0. And the value of a negative number, the sign bit will be 1, 1, 0, 1. And the BCD format of 4 is 0, 1, 0, 0. So our final answer will be this one. So let's move on with the packed decimal format. So the packed decimal format or PDF, it also uses 1 byte or 8 bits binary representation. But the difference is it is for 2 digits. Again, it is for 2 digits. The least significant bit contains the sign bit, meaning the sign bit is placed at the end. Again, for the positive numbers, the sign bit will be 1100, and for the negative numbers, it will be 1101. Let's try some examples. What is the PDF of positive 137? So let's 1. Again, the PDF is for 2 digits, so we have 1 and 3. And then the sign bit is the least significant bit, so it will be at the end. 7, positive 7. So for this value, the BCD format of 1 is 0, 0, 0, 1. And for 3, the BCD format is 0, 0, 1, 1. For the next digit, 7, the BCD format of 7 is 0, 1, 1, 1. And this is a positive number, so the sign bit will be 1, 1, 0, 0. So our final answer will be this one. Let's try another example. So what is the PDF of negative 2895? So again, we have 5, the last digit together with the sign, which is negative. And then we group 2 digits, 8 and 9. And then we have 2. And we all know that the PDF is for 2 digits, so we will put 0 next to 2. So that we will be getting, so the BCD format of 0 is 0, 0, 0, 0. And the BCD format of 2 is 0, 0, 1, 0. For 8, for 8 and 9, the BCD format of 8 first is 1, 0, 0, 0. And for 9, it will be 1, 0, 0, 1. For the last digit, the BCD of 5 is 0, 1, 0, 1. And the value of sign bit for negative is 1, 1, 0, 1. So our final answer will be this. So let's move on to the absolute value or the sign magnitude. The absolute value or the sign magnitude is used to represent positive and negative numbers. And the most significant bit or the first bit contains the sign bit. In this case, the value of the sign bit for positive numbers is 0, and the value of the negative numbers is 1. So the syntax for this is, the first bit is the sign bit, and it is followed by the binary form. So let's try some examples. So what is the sign magnitude representation of positive 102? So we know that this is a positive number, so the sign bit will be 0. And to get 102, we need to add 64, 32, 4, and 2. So our value for 102 will be 1, 1, 0, 0, 1, 1, 0. So our final answer will be 011001110. So let's try another example. So what is the sign magnitude representation of negative 79? This time it is a negative number, so our sign bit will be 1. And in order to get 79, we need to add 64, 8, 4, 2, and 1. So our value for this will be 1, 0, 0, 1, 1, 1, 1. So our final answer will be 1, 1, 0, 0, 1, 1, 1, and 1. Now let's have the ones complement. So for the ones complement, it is just a subtraction of ones, or you can invert the given binary number. Meaning, the 0 will be 1 and the 1 will be 0 to get the ones complement. So let's apply this in some examples. So what is the ones complement of 1, 1, 0, 1? So let's try the first method, the subtraction of ones. So there are 4, then ones, because we have 4 bit. So we will subtract 1, 1, 0, 1. So 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. So this is our ones complement. You can see if we invert the given number, 1 and 1 became 0, and 0 became 1, and 1 became 0. So this is our final answer. So let's try another example. What is the ones complement of 1, 0, 0, 1, 1? This time we have a 5 bit, so 5. Then subtract the given 1, 0, 1, 1. So 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 0 is 1. Then 1 minus 0 is 1. 1 minus 1 is 0. So again, if we look with the given, 1 became 0, 0 became 1, 0 became 1, 1 became 0, and 1 became 0. So this is our final answer for the ones complement. Now let's move to the twos complement. So in order to get the twos complement, first we have to get the ones complement of the given binary number. Then after we got the ones complement, we will add 1 to it. So let's try to apply this to some examples. So let's try to get the twos complement of 1, 0, 0, 1. So the ones complement of this will be, invert the number 0, 1, 1, 0. And to get the twos complement, we will add 1 to the ones complement. So 0 plus 1 will be 1, then bring down the other bits. So the twos complement of 1, 0, 0, 1 is 0, 1, 1, 1. Let's try another one. So what is the twos complement of 1, 0, 1, 1, 0, 0? So first again, let's get the ones complement of this. Let's just invert it. So we will be having 0, 1, 0, 0, 1, 1. And then we will add 1 to this. So 1 plus 1 is equals to 0, and then carry 1. Then 1 plus 1 again is equals to 0. and then we will be carry 1. Then 1 plus 0 is 1. Then we bring down the others. So the 2's complement of 1, 0, 1, 1, 0, 0 is 0, 1, 0, 1, 0, 0. Now let's move on to the second part of the numeric data representation. In this, we will be discussing the fixed point numbers and the floating point numbers. So first, let's have the fixed point numbers. For the fixed point numbers, the positive numbers, we just need to get the sign magnitude representation, while for the negative numbers, we just need to get the 2's complement. So let's try this to some examples. So let's have the positive 42. So for positive numbers, we will be getting the sign magnitude. So for the sign bit, this is a positive. The sign bit is 0. And to get the magnitude of 42, it is 32 plus 8 plus 2. So the value for this will be 0, 1, 0, 1, 0, 1, 0. So this is the answer for the positive 42. So now let's try the negative 42. For the negative numbers, we need to get the 2's complement. And to get the 2's complement, we first need to get the 1's complement. The 1's complement of 42 is 1, 1, 0, 1, 0, 1, 0, 1. And then for the 2's complement, we will add 1. So 1 plus 1 is equals to 0. Then we carry 1, and 1 plus 0 is 1. Then we bring down everything. So 1, 0, 1, 0, 1, and 1. So the answer for this is 1101, 10110. Let's try another example. Again, for the positive numbers, sign magnitude representation. The sign bit will be 0. And for the 36, we need to add 32 plus 4. So the value for this will be 0, 1, 0, 0, 1, 0, 0. So this is our answer. Next, the negative 36. Again, we need to get the 2's complement. But first, we have to get the 1's complement. So the 1's complement of for the negative 36 is 1, 1, 0, 1, 1, 0, 1, and 1. To get the 2's complement, we will be adding 1. So 1 plus 1 is 0. Then we carry 1. Then 1 plus 1 is, then we carry again. Then 1 plus 0 is 1. Then we bring down everything. And this is our answer. 1101100. Now let's have the floating point numbers. So for the floating point numbers, we have a is equals to positive negative m multiplied to r raised to e, where a is the floating point representation, r is the base, e is the exponent, m is the mantissa, positive or negative is our sign magnitude. So for the floating point numbers, the sign bit contains 1 bit, the exponent contains 8 bits, and it is followed by the 23 bits mantissa. So here is the step in order to determine the floating point numbers. The first step is to convert the given number to its binary form. The second step is to represent the binary form into its scientific notation. Next is to determine the sign bit by checking if the given number is a positive or a negative number. The fourth step is for the exponential bits. We add e from the scientific notation. We add it to the 127, then convert its sum to its binary form. Lastly, for the mantissa contains the bits after the decimal point in the scientific notation. If it doesn't reach 23 bits, add zeros to it. So let's try some examples while applying the following steps. So we have 17.125. So again, the first step is to convert it to its binary form. So we already know how to convert this. For 17, we just need to divide this to 2, and then we will get 1, 0, 0, 0, 1. For the decimal, we just need to multiply this to 2, and we will get 0, 0, 1. So the next step is to get the scientific notation. So to get the scientific notation, all we need to do is to shift the decimal point until we reach the last non-zero value. So it will be equal to 1.00001001 times 2 raised to 4. So our exponent is 4. Then the third step is for the sign bit. This is a positive number, so our sign bit will be 0. The fourth step is for the exponent bits. So as I have said earlier, our exponent is 4. So we add 4 to 127. 4 plus 127 will be equal to 131. And then we convert the sum to its binary form, and we will get 1, 0, 0, 0, 0, 0, 1, 1. The last step is for the mantissa. We said that the mantissa are the bits after the decimal point from the scientific notation, so it will be 0, 0, 0, 1, 0, 0, 1. Right now, the mantissa is 7 bits, but we need it to be 23 bits, so we will be adding 16 zeros to it. 16 zeros. And our final answer for this will be this one. So this is our sign bit, which is 0. So this is our exponential bit from this one. And this is our mantisa, together with the 16 zeros. Now let's move on to the data representation for non-numeric or the character representation. We will run through to some other character representation, but we will focus with the ASCII code and the ABCDIC code. So first we have the International Standards Organization or the ISO. It is a character code of 7 bits based on the ASCII code. And since it is 7 bits, it does not use a parity bit or a check bit. Next, we have the Japanese Industrial Standards or the JIS. A JIS 7-bit code is used for Romaji. A JIS 8-bit code is used for katakana. And the kanji code, which is composed of 16 bits, is for hiragana and kanji. Next is we have the Unicode. It is a 2-byte or 16 bits code system presented by Apple, IBM, Microsoft, and other US companies. It can be implemented by different character encoding. It also assigns a unique code to every character and symbols. It is adopted by the ISO as an international standard graph. We have the American Standard Code for Information Interchange or the ASCII code. So ASCII code is a character code consists of 8 bits. 7 bits is for the alphabet, numeric, and other characters, while the remaining 1 bit represents the parity bit. So what is a parity bit? A parity bit is also known as the check bit. There are 2 kinds of parity bit. There is the even parity bit and the odd parity bit. To determine the parity bit, all you need to do is count the presence of ones. So here is an ASCII table of each character with its corresponding ASCII code. Now let's have an examples. What is the ASCII equivalent of lip? So here we have capital L, small letter E, small letter A, capital P, and we have the even parity bit, the odd parity bit, and here is the magnitude. So based on the table that we have shown earlier, capital letter L has an ASCII code of 76. Small letter E has an ASCII code of 101. Small letter A has an ASCII code of 97. And capital letter P has an ASCII code of 80.
Now we will be converting it to its binary form. And since it is a 7-bit code, the highest placement value will be 64.
So for capital letter L, we have 76. It is equivalent to 1, 0, 0, 1, 1, 0, 0. Because if we add 64, 8, and 4, the sum of it will be 76. Next, we have letter E. Its ASCII code is 101, so it will be equal to 1, 1, 0, 0, 1, 0, 1. And again, 64 plus 32 plus 4 plus 1 is equals to 101. Next is we have letter A, and its ASCII code is 97. Then its equivalent will be 1, 1, 0, 0, 0, 0, 1. And lastly, for the capital letter P, we have 80, and it will be equal to 1, 0, 1, 0, 0, 0, 0.
And now we have the 7-bit ASCII code for the word. The next thing we need to do is to determine the parity bit or the check bit.
First bit contains the parity bit. And we have said earlier that there are two kinds, the even parity bit and the odd parity bit. First, we will determine if we use the even parity bit. So using the even parity bit, we will count the number of ones to check if it is even or not. So for capital letter L, we have 1, 2, and 3. So it is not even. So our even parity bit will be 1. Next, we have for the letter E, we have 1, 2, 3, and 4. So 4 is an even number, then our even parity bit will be 0. Next, for the small letter A, we have 1, 2, and 3. Therefore, our even parity bit will be 1. And lastly, for letter P, we have 1, 2. 2 is an even number, therefore our even parity bit will be 0. So this will be the ASCII equivalent together with this one if we are using the even parity bit. What if we are asked with the odd parity bit? Just like the even parity bit, we will count the number of ones and check if it is odd. So for capital letter L, we have 1, 2, 3. So our odd parity bit will be 0 because 3 is an odd number. For small letter E, we have 1, 2, 3, and 4. Therefore, our odd parity bit will be 1 to make it odd. For letter A, we have 1, 2, and 3. So our odd parity bit will be 0. And lastly, for letter P, we have 1 and 2. So our odd parity bit will be 1. So this will be the ASCII equivalent for LIP. Now let's move on to the last part, which is the extended binary coded decimal interchange code, or the EBCDIC. The EBCDIC is a character code consisting of 9 bits. The 8 bits represent the zone and the digits, while the 1 bit is for the parity bit. Just like in the ASCII code, we have a parity bit, which we all know as the check bit. So here is the ABCDIC table. Here is the characters, the corresponding zone, and the corresponding digits. Let's try to complete an example. What is the ABCDIC equivalent of CCIS? So we have an even parity bit, odd parity bit, the zone, the digits. So let's start with the capital letter C. So based from the table that we have shown earlier, capital letter C, we will use a parenthesis here. The corresponding zone for capital letter C is 12. And the corresponding digit for it is 3. For the small letter C, the zone for it is 8. And the corresponding digit is 3 also. For small letter I, the zone is 8, and the corresponding digit is 9. And lastly, for S, the zone for S is 14, and the digit is 2. This is all based from the table that we have shown earlier. So for letter C, capital letter C, the zone for capital letter C is 12, so we will have 1, 1, 0, 0. Because again, 8 plus 4 is equals to 12. And the digit for it is 3, so we have 0, 0, 1, 1. So for the small letter C, the zone is 8, so we will have 1, 0, 0, 0. And for the digit, it is also 3, so we will also have 0, 0, 1, 1. Next is we have the small letter I. The zone is also 8, so we will have 1, 0, 0, 0 as well. And for the digit is we have 9, so it will be 1, 0, 0, 1, because 8 plus 1 is equals to 9. And lastly is for letter S, the zone for letter S is 14. So we will have 1, 1, 1, 0. Because 8 plus 4 plus 2 is equals to 14. And for its digit, it is 2. So we have 0, 0, 1, 0. And just like in the ASCII code, we have parity bits. First, let's determine the even parity bit by again counting the presence of ones. So for letter C, we have 1, 2, 3, and 4. So the even parity bit will be 0. And for the small letter C, we have 1, 2, and 3. Therefore, our even parity bit will be 1 to make it even. Next is we have letter I, 1, 2, and 3. Also, the even parity bit for this will be 1. And for letter S, we have 1, 2, 3, 4. So the even parity bit will be 0. So this will be the EBCDIC equivalent of CCIS if we are using the even parity bit. What if we are using the odd parity bit? So again, we just count the presence of ones. 1, 2, 3, and 4. Since it is not odd, the odd parity bit will be 1. Next, for the small letter C, we have 1, 2, and 3. Since 3 is an odd number, the odd parity bit will be 0. Next, for the letter I, we have 1, 2, and 3 also. So the parity bit will be 0. Lastly, for the letter S, we have 1, 2, 3, and 4. Therefore, our parity bit will be 1 to make it odd. And now, this is our EBCD equivalent of CCIS when we use the odd parity bit. So that is how you determine the ABCDC equivalent. And that ends the lesson for this video. Thank you and have a nice day.